And the crazy thing is, Pinterest processes billions of visual searches every single month. Billions! That's not just people looking for recipes. That's people pointing their phones at like a cool chair and saying, "Find me that chair."
Billions? That's staggering. So we're not just talking about reverse image search, like finding the source of a meme. This is a whole different level of sophisticated image understanding.
Exactly. Imagine the infrastructure needed to handle that scale, and the cost of getting it wrong. Think about it. If Pinterest visual search fails too often, people stop using it. They go back to typing in keywords, and Pinterest loses a huge advantage.
And that advantage is what exactly? Discoverability? Being able to surface relevant products and ideas that users wouldn't have found through text alone?
Precisely. It unlocks serendipitous discovery. You see something you like, you point your phone at it, and bam! Pinterest shows you similar items, related ideas, and maybe even where to buy it. Without visual search, Pinterest is just another image bookmarking site. With it, it's a visual discovery engine.
Okay, so let's break down how this actually works. At a high level, what are the key components of a visual search system, like the one Pinterest uses?
All right, picture this. It's like a library, but instead of books, it's full of images. And instead of a card catalog, it has a super smart index that understands what's in the images. The first step is feature extraction. We need to turn each image into a numerical representation, a fingerprint that captures its visual essence. This is typically done using deep learning models, specifically convolutional neural networks, or CNNs.
CNNs. We've talked about those before. They're good at identifying patterns, right? Edges, shapes, textures. But how does that translate to finding similar images?
That's where the magic happens. The CNN outputs a high-dimensional vector, a long list of numbers that represents the image's visual features. This vector is the image's embedding. Images with similar embeddings are considered visually similar. Think of it like this. If you plot all these image embeddings in a multi-dimensional space, images that are close together are visually alike.
Okay, I'm following. So you have a bunch of images, you run them through a CNN to get their embeddings, and then you store those embeddings. But how do you actually search? Do you compare the query image's embedding to every single embedding in your database? That sounds incredibly slow, even with optimized hardware.
You're absolutely right. That's where approximate nearest neighbor search comes in. Instead of exhaustively comparing the query embedding to every single embedding in your database, ANN algorithms use clever data structures and indexing techniques to quickly find the approximate nearest neighbors. It's a trade-off between speed and accuracy. You might not find the absolute closest image, but you'll find something very close very quickly.
Give me an example. What kind of data structures are we talking about?
One popular technique is called hashing. Imagine you have a bunch of buckets and you want to distribute your images into these buckets based on their embeddings. Hashing algorithms create a function that maps similar embeddings to the same bucket. So when you search for a similar image, you only need to compare your query embedding to the images in the same bucket. It's like searching for a book in a library by first looking at the section it belongs to.
Okay, that makes sense. So feature extraction with CNNs, then ANN search using techniques like hashing. What's the third key component?
Context. Raw visual similarity is powerful, but it's not enough. We need to incorporate contextual information to improve the relevance of the search results. Think about Google Lens. It doesn't just find visually similar images, it tries to understand what's in the image and what you're trying to do.
So how do you add context? Are we talking about natural language processing?
Not necessarily NLP in the traditional sense, although that can play a role. More broadly, it's about incorporating metadata, user behavior, and other signals to refine the search results. For example, if you're searching for a picture of a dress, Pinterest might consider your past interactions with similar dresses, the popularity of the dress on the platform, and the text descriptions associated with the image.
So it's a combination of visual similarity and personalized recommendations.
Exactly. Think of it like Netflix recommending movies. They don't just recommend movies that look visually similar to what you've watched. They consider your viewing history, your ratings, and the overall popularity of the movie. Visual search systems do the same thing, but with images.
That makes sense. So feature extraction, ANN search, and contextualization. But wait, doesn't the choice of CNN architecture significantly impact the performance of the entire system? What if you choose the wrong CNN?
That's a critical point. Here's where it gets interesting. The choice of CNN architecture is absolutely crucial. A poorly chosen CNN can lead to poor feature embeddings, which in turn degrades the accuracy of the entire visual search system. It's like building a house on a weak foundation.
So, how do you choose the right CNN? Is it just trial and error?
Not exactly. There are a few key considerations. First, you need to consider the size and complexity of the CNN. A larger, more complex CNN can capture more nuanced features, but it also requires more computational resources and more training data.
Okay, so size, complexity, and training data. But what about the specific architecture? Are there specific CNN architectures that are better suited for visual search than others?
Yes, absolutely. Architectures like ResNet, Inception, and EfficientNet have proven to be very effective for image recognition and feature extraction. These architectures incorporate techniques like residual connections and attention mechanisms that allow them to learn more robust and discriminative features.
So you're saying that the choice of CNN architecture is not just about accuracy on a benchmark dataset, it's also about the quality of the feature embeddings it produces and how well those embeddings lend themselves to efficient ANN search.
Precisely. And here's the counterintuitive part. Sometimes a slightly less accurate CNN can actually lead to better visual search results because its embeddings are more compact and easier to index. It's all about finding the right balance between accuracy, efficiency, and scalability.
That's fascinating. So what's one thing that most engineers get wrong when building visual search systems?
They underestimate the importance of data quality. Garbage in, garbage out. If your data is noisy, biased, or unrepresentative, your visual search system will perform poorly, no matter how sophisticated your algorithms are. It's like trying to train a self-driving car on a dataset of blurry, low-resolution images.
Okay, that makes sense. So, what are 3 practical takeaways for software engineers who are interested in building their own visual search systems?
First, start small and iterate. Don't try to build a Pinterest-scale visual search system from day one. Start with a small dataset, a simple CNN architecture, and a basic ANN search algorithm. Then, gradually increase the complexity of your system as you learn more. It's like building a startup. Start with a minimum viable product and iterate based on user feedback.
Okay, start small and iterate. What's the second takeaway?
Second, focus on data quality. Spend time cleaning and curating your training data. Remove duplicates, correct errors, and ensure that your dataset is representative of the types of images you'll be searching for. It's like weeding your garden. You need to remove the weeds before your plants can thrive.
And the third takeaway?
Third, experiment with different CNN architectures and ANN search algorithms. There's no one-size-fits-all solution. The best choice depends on your specific use case, your data, and your computational resources. Don't be afraid to try different things and see what works best. It's like cooking. Experiment with different spices and seasonings until you find the perfect recipe.
Great. So, start small, focus on data quality, and experiment. Any final thoughts?
Just remember, visual search is not just about finding visually similar images, it's about understanding the world through images, and that's a pretty powerful capability.